Ways that we handle acid-base reactions. One way is if it's metathesis. If it's metathesis, then we'll go ahead and use the metathesis method. This is going to be a metathesis reaction. This is AB plus CD pattern. AB plus CD pattern is going to form what?
Calcium chloride.
Calcium chloride. What's the formula for calcium chloride?
CaCO2.
And is it an insoluble solid or a soluble solid? It's soluble. Chlorides are soluble except for silver, lead, and mercury. So CaCl2 plus carbonic acid, which is H2CO3. But the thing about H2CO3 is it's unstable, so we have to draw this arrow here showing it immediately decomposes into H2O liquid plus, and so this is the effervescence, this is the carbon dioxide gas. What's the driving force for this particular reaction?
Gas formation.
Yeah, gas formation, you could say. So gas, CO2 gas. Okay, anything else?
Could you say it's going from a stronger acid to a weaker acid?
Yeah, we could say it's going from a stronger acid, HCl, to a weaker acid. What's the weaker acid?
Decomposing carbonic acid.
Yeah, and so this would be the weaker acid, carbonic acid, which spontaneously decomposes. And so stronger acid, HCl, the weaker acid, carbonic acid. And the carbonic acid decomposes in water and CO2. Is water an acid? No, well, water is really amphoteric, but it turns out that CO2 is an acid. Did you know CO2 is an acid? It doesn't look like an acid because there's no H. But CO2 is an acid. It's a Lewis acid in this case. And so we could have gone to CO2. It could have been stronger acid HCl to weaker acid CO2. If we wanted to, but we could just go to carbonic. That's adequate. And so a driving force for this occurs. Calcium carbonate is a solid. Carbonates are insoluble. So we got gas formation. Let's balance this since there's a driving force. When we balance it, I'd like to leave carbonic acid here because it's easier to balance that way. One carbonate, two hydrogens. We only have one hydrogen here, so we'll need two HCl's, and then two chlorides, and so now it's balanced. This we call the CE. Okay, let's go ahead and write the IE, the ionic equation. So we have the complete or conventional equation. We go to the ionic equation. What is it? Yeah. So in the ionic equation, do we ionize HCl or leave it? We ionize it. What does it ionize to?
H plus Cl.
H plus Cl minus. Now, when we ionize it, we don't want to lose any H plus. How many H pluses did we start with? We started with 2, so better not lose any. And so we're going to put 2 here. And then Cl's. How many Cl's did we start with? 2. And so we'll need 2 Cl minuses. Okay, now all atoms are accounted for. Calcium carbonate, do we ionize that or do we just leave it alone? As is. Ionize or leave as is? Yeah, we leave it alone. Because we know we ionize what? We ionize the strong electrolytes. Strong electrolytes consist of the strong acids. Calcium carbonate's not a strong acid. Strong base. Calcium carbonate's not a strong base. And a soluble salt. Well, calcium carbonate is an insoluble salt. And so we don't do anything to that. We'll just leave it. Calcium chloride, do we ionize that or leave it? We ionize it. It's going to ionize into what? Calcium ions and chloride ions. Does that look good? No, that doesn't look good because we had 1 calcium, 2 chlorides, and we lost 1 chloride, so we'll just bump that up to 2. Now all the chlorides are accounted for. Okay, carbonic is not there. This is going to be replaced by water. Do we ionize water? No. It's H2O liquid. Do we ionize CO2? No. Yeah, CO2 is not a strong acid, strong base, or soluble salt. Okay, then we go on to the net ionic equation. Net ionic equation, we get rid of spectators. So are there any ions that didn't participate in this reaction? Any spectators? Yeah, chlorine or chloride. 2 chlorides here, 2 chlorides there, so we'll have 2H plus, get rid of the chlorides. Those are plus calcium carbonate solid goes to calcium 2 plus H2O liquid plus CO2 gas. And so one way to check to make sure that the equation is balanced is to check the atom balance first. 2 hydrogens, 1 calcium, 1 carbon, 3 oxygens, 3 oxygens. So the atoms are balanced. But you also have to make sure that the charge is balanced. So the net charge on the left would be plus 2 and 0, so plus 2 on the left, has to equal the net charge on the right, which is plus 2 and 0 and 0, so it's plus 2. Plus 2 and plus 2, the charges are balanced. And so it looks good, and we have the driving force in this case. Okay, this is an example of metathesis, double replacement. And again, if it can react in a metathesis way, we'll try to. What's this next reaction, though? If we look at the next reaction, it's going to be HCl plus zinc, solid, zinc metal. Does that look like an acid-base reaction to you? Or what kind of reaction does that look like to you?
Redox.
This looks like redox, yeah. In fact, it is. This is a single replacement style reaction. Would single replacement work? Yeah, it should work. Zinc is a good reducing agent, better than water. And then H plus is a good oxidizer, better than chloride. Chloride's not an oxidizer, chloride's a reducer, and water. And so this is actually going to fit the single replacement A plus BX pattern. A plus BX yields what? Actually, I wrote it backwards, but A plus BX here, BX plus A yields what? Or we could do this using the chart method, you know. But I know this isn't going to be an exception because the best oxidizer should be H plus. If you include water in there, and the best reducer should be zinc. Chloride's another reducer, water is another reducer. Water is also another oxidizer. And so what it yields is zinc chloride, ZnCl2, and hydrogen gas. A plus BX yields AX plus B. Is there a driving force for this reaction?
Gas formation.
Gas formation? Gas formation is a driving force for metathesis and acid-base, but not for redox. Gas formation does not work for redox. Precipitation does not work for redox. Stronger to weaker acid does not work for redox. What works for redox? Only, yeah, stronger oxidizer to weaker oxidizer and stronger reducer to weaker reducer. Well, the reducers are known to be ranked in something called the activity series. This is the activity series. The most active is lithium. And so this is the activity series based on reducing strength. You know, reducing strength is, you know, the easiest to oxidize would be lithium. Then it gets harder and harder to oxidize. So this is the most active, and then the least active is at the bottom. So what we're going to do is we're going to compare the two elements, zinc versus hydrogen. Here's zinc. It's fairly active. And down there is hydrogen. So if we were to use activity series, what we would say this is that zinc is more active than hydrogen. And therefore, there's a driving force. We're going from a more active to a less active reducing agent or element. In other words, stronger reducing agent to weaker reducing agent. So there's a driving force for this. We just got to balance it now. And to balance it, looks like we need 2 HCl's, and that should do it. There. So this is an example of a redox reaction. Acids can participate in redox reactions. The reason acids can participate in redox reactions is because H+. All acids have H+. H+ is a moderate oxidizer. And so it's an oxidizer. It's not acting as an acid, it's acting as an oxidizer. If we're acting as an acid, then acids are, you know, proton donors or hydrogen donors. This is acting as an oxidizer. And it's the H+ that's acting as it, although we need to check the anion too. Check the anion here. In metathesis, we need to check both the cation and the anion sequence combinations. Must check anion and water for potential reactivity as well. You know, because sometimes the anion, like nitrates, are even more powerful oxidizers than the cation H+. Or sometimes water is a more powerful oxidizer than both. Depends on how weak it is. All right, let's go ahead and do this is the CE. Let's do the IE for this. The final exam is going to be comprehensive, but it's not like going to be half, you know, chapter 17, 18, 19. You know, it's going to be kind of spread out over all the chapters. If it's spread out, let's say 60 to 70 questions, and spread out over all the chapters, you're looking at 5 to 10 questions per chapter. Something like that,
Is it going to be all multiple choice or just most?
It's all multiple choice, the final. And then there's going to be a bonus. The bonus is not going to be multiple choice. The bonus is going to be reactions like this, you know, nomenclature. You got to write down the correct formula, and then you got to predict the reactions here. So for this particular one, we could also, that's a CE, we could also do the ionic equation here. So if there's an opportunity to do the ionic and then ionic, we'll be asked to do that. And so for the ionic equation for this, HCl, do we ionize or leave it alone? Okay, what does it ionize into? H+ and Cl minus. Did we lose any atoms going from the CE to the IE? Yeah, 2. We got to make sure we have 2 H+ and 2 Cl minuses to keep everything properly balanced. The zinc. What do we do with the zinc? Do we ionize that? No, it's just zinc, solid. There's no charge on that. How about zinc chloride? Do we ionize that? Yeah. So this is going to ionize into what?
CO2 plus 2 CO minus.
Okay, then we look for spectators. You see any spectators? Chloride. So chloride's a spectator. It doesn't change going from the left to the right side. So the reaction is 2H pluses attack the zinc solid. The 2H pluses are going to oxidize the zinc to form Zn2 plus H2 gas. This is balanced. We got two hydrogens, one zinc, and the charge is balanced. 2 times plus 1 is plus 2, and then plus 2. Plus 2. So this is a different type of reaction there. And so this type of reaction is discussed in, obviously, chapter 19, the earlier chapter that we had, redox. But this is your more proper acid-base reaction here. But acids do have that redox property, so be aware of that. All right, so here, let's take a look at this reaction here. What I'm going to do is I'm going to just rewrite this up on the board here. If I take a look at ammonia, what is ammonia? Is it an acid, is it a base, or is it both? Ammonia, an acid, base, or both? Yeah, both is the correct answer here. Here's ammonia. Here. Here's ammonia here. And so this is ammonia as what? A base or an acid? An acid. And so ammonia is an acid. It's near the bottom. You know, the strongest acids are there. So ammonia is very weak. But as ammonia as a base, it's decent. You know, it's not strong, but it's moderate. And so it's a much better base than it is an acid. But we don't know how it's going to react. You know, I don't know, is it going to react as an acid or is it going to react as a base? Well, it depends on what you react it with. And so we'll just say acid or base. Then we have some water here. Water can either go either way, acid or base. And so we have two acids and two bases. Which acid is stronger? Ammonia or water? Yeah. And so when we look at the chart here, ammonia versus water, which one's stronger? Water is stronger. And so what that means is that the water will act as the acid. Okay, let's take a look at the bases. I'm going to compare the two bases. Oh, shoot. We compare the two bases, ammonia versus water. Which one's stronger? These are the bases on this side. Scroll up. Okay, here's ammonia. Here's water. Which one's a stronger base? Ammonia. Ammonia is quite a bit stronger than water as far as base properties go. So this will be the base. And so what's going to happen in the reaction between ammonia and water? Well, the most likely reaction to occur, and it depends on if there's a driving force present or not, is what do bases do? Bases take hydrogen ions. from acids. Acids lose hydrogen ions to the base. And so this base, ammonia, is going to take this hydrogen here. When it takes it, it's not going to take the electrons too. It's just going to take the hydrogen ion, and it's going to leave behind the electrons like that. And so this lone pair will form a new bond to the hydrogen here. So we end up with this, NH4. When you look at the formal charge on nitrogen is positive, and the whole thing carries a plus charge. So it forms ammonium. So ammonia takes a proton or a hydrogen ion from water and forms ammonium. Water is going to lose that hydrogen ion, but it's going to retain the electrons. And so what we're going to have for the other product looks like this. This oxygen is going to have a negative charge, and the whole thing carries a negative charge. And so we form ammonium and hydroxide. All right, so we had our base and our acid. In order to figure out the driving force, we need to know the base and the acid in the reverse direction. So if we go backwards, what is the base and the acid in the reverse direction? There are two ways we could do this. One way is we could look, bases take the hydrogen. So if we go backwards, who's taking the hydrogen? If ammonium takes a hydrogen, then we'd end up with 4 plus 1. We'd end up with 5 hydrogens. If hydroxide takes the hydrogen, we'd end up with 2 hydrogens, 1 oxygen, H2O. So who takes the hydrogen? Yeah, hydroxide. So this is the base, and this would be the donor, the hydrogen ion donor, the acid.